Welcome to the Western Hemisphere Virtual Symplectic Seminar. For today's speaker, we're very happy to have Oliver Edtmair from UC Berkeley tell us about PFH spectral gaps and quantitative C-infinity closing lemmas.
Okay, I hope you can see the slides. Is that correct? All right, yeah. So we'll talk about spectral gaps in PFH and how to use them to show smooth closing lemmas. And that's based on a joint paper with Michael Hutchings. So before I start, I should point out that there's an independent but very related project by Dan Christopher Gardner, Rohil Prasad, and Poyu Shang. And I think Rohil actually gave a talk about this early in the seminar today, if I'm not mistaken. Okay, so I want to start with a short introduction to closing lemmas in general. So we take a closed manifold M, it's not yet symplectic, and we take a diffeomorphism of that manifold phi. And then let's consider a recurrent point of that diffeomorphism. There's a point P that has the property that for any arbitrarily small open neighborhood of that point, we can always find a sufficiently large iteration of phi such that P gets mapped back into that open neighborhood. So the point P returns infinitely often arbitrarily close to itself, but it might never close up. And then the question you want to ask is whether it's always possible to make this recurrent point with an honest periodic point a very small perturbation of the diffeomorphism phi. And so it turns out that if small perturbation means small in the C0 topology in this space of diffeomorphisms, then the answer is yes, and it's actually kind of easy to show. So that's a couple of lines to prove that. But it turns out that if small means small in the C1 topology in this space of diffeomorphisms, then that question becomes a whole lot harder. And this very famous theorem by Charles Pugh from the 60s that says that it's also possible to close it up in the C1 topology, but that's a very hard theorem compared to the C0 case. And then if we increase the regularity even further, say at least 2, CK topology for K at least 2, then the situation is kind of largely unknown. And in fact, it's one of problems on Smail's list of open problems. Okay, so here now things become symplectic. So Pugh and proved a symplectic version of the C1 closing lemma. So here the point is that if you have a symplectomorphism of a closed symplectic manifold, then by Poincare recurrence, almost every point is recurrent. So we can create periodic points pretty much everywhere in the manifold where we want them. So we take any non-empty open set, and we can always find a C1 small perturbation of the symplectomorphism that produces an orbit through that open set U. And an important application of that is the generic density theorem, which says that if we now take a C1 generic symplectomorphism, then the closure of the set of its periodic points is the whole manifold. So that's so the hard step here is the C1 closing lemma, and then this is a corollary of that. Okay, so here's the starting point for today's story. So it's a pretty awesome theorem that Asaoka-Irie proved a couple of years ago. So it says if we take a closed free manifold with a rape flow on it, then we can pick any non-empty open set, and we can always find a perturbation of the contact form that's now small in the C-infinity topology. It's supported inside the open set, and its new rape flow has an orbit, a rape orbit, that closed rape orbit intersects the open set U. So in the context of three-dimensional rape flows, we have the C-infinity closing lemma, which in general is wide open. So an important ingredient of the proof of this C-infinity closing lemma is embedded contact homology, and in particular the Weil law for the ECH spectral numbers, which was proved by Christopher Gardner, Hutchings, and Ramos. And so roughly speaking, this Weil law says that the ECH spectral invariants in the limit can recover the contact volume. And what it means is that if we have a family of perturbations of the contact form supported in our small set U. And if we assume that that family of perturbation actually changes the contact volume, then that must have produced orbits. Because if it didn't produce orbits, then all the spectral invariants would stay the same, and then the contact volume would have to stay the same by the Weil law. And so what is particularly remarkable about that is that so in Pugh's C1 closing lemma, he put a lot of work into constructing a very specific C1 perturbation that produces an orbit. And here this says that pretty much whatever you do is forced to produce orbits. Just has to change the volume. That's not a big requirement. Okay, and then again, this has a corollary that a C-infinity generic contact form in a closed tree manifold now has a dense set of closed ray orbits.
I'd make a comment about Pugh's remark, or actually a question maybe too. If I understand correctly, Pugh actually closes the orbits, right?
Yes.
So here this doesn't say you can close a recurring orbit. It just says you perturb and you know there exists a periodic orbit nearby.
So I think the trick you can do is that if you close a nearby orbit, you can always conjugate the thing to move the new closed orbit to where the old one was, and that's good enough.
Yeah, so then you have, but you haven't really closed the old orbit.
Well, yes, no, first you close a nearby orbit and then you conjugate and then you have a perturbation that closed the old one.
Okay, so this, you're saying this actually closes the orbit.
Yeah, so I think, that's actually also how Pugh's lemma works. He first goes to a nearby orbit and then he does the conjugation trick and then it's the actual orbit, yes.
Oh, but then this new orbit that you're creating away from the open set, away from where the small perturbation is, it might have been some other orbit. You see what I'm saying? I'm not sure if this actually closes the orbit or. Well, maybe this is. But you seem sure that it does close the orbit, so maybe I'm mistaken.
Yeah. Well, maybe we can discuss that.
We could talk about that later.
All right. Okay. So we have this awesome result by Irie, which is kind of the starting point of today's story. So shortly after that result, Asaoka-Irie used the closing lemma for three-dimensional rate flows to show a smooth closing lemma for Hamiltonian diffeomorphisms of closed surfaces. So if we have a closed surface and the Hamiltonian diffeomorphism of that, we can again fix any arbitrarily small non-empty open set, and we can produce orbits through that set by a C-infinity small Hamiltonian perturbation of the original Hamiltonian diffeomorphism. And that really is a consequence of the closing lemma for 3D rate flows. So they use some kind of open book construction to encode the dynamics of the Hamiltonian diffeomorphism as the dynamics of a three-dimensional rate flow and then apply the rate flow result by Irie. And then again, there's a corollary that says that the C-infinity generic Hamiltonian diffeomorphism of the closed surface has to have a dense set of periodic orbits. Okay, and so in today's talk, I want to extend this result by Asaoka-Irie in two different directions. So first, I want to make the closing lemma quantitative, and I will say in a moment what that's supposed to mean. And then the second generalization is to go from Hamiltonian surface diffeomorphisms to more general area-preserving surface maps that are not necessarily Hamiltonian. Okay, so here is our setting. So sigma omega will always be a closed surface of some genus with an area form and total area capital A. We take a symplectomorphism that will always be phi, and we fix some small non-empty open subset U inside our surface. Okay, so now if we start with phi, we want to now consider Hamiltonian perturbations of that diffeomorphism. And I will use this notation here that if I'm given some time-dependent Hamiltonian, that will induce a time-one Hamiltonian flow. And my Hamiltonian perturbation of phi, which I call phi h, is simply the composition of phi with my Hamiltonian diffeomorphism. Okay, and so now if we take our open set U and let's take some Hamiltonian which with support inside that open set, then we actually consider a whole family of Hamiltonian perturbations where we use this parameter tau to change kind of the size of the perturbation. So if tau is equal to 0, we just get back phi, and then if we increase tau, we can make the perturbation bigger. And then the question I want to ask is that if I fix some interval, 0 to delta, and I look at all the perturbations for tau in that interval, then that term of perturbations, it can kind of create and destroy orbits that intersect U. And then the question one can ask is, within that family of perturbations, what was the minimal, like, did there have to be a periodic orbit showing up that intersects U? And if so, what can we say about the period of such orbits? Okay, and so before I state now the first version of the quantitative closing lemma, I need to be quantitative about the size of the Hamiltonian. So here's a picture of the kind of Hamiltonians I want to consider. So it's just some non-negative little bump that's supported inside my open set U. And then it will be useful to somehow kind of control or measure give a rough measurement of the size of the support of this bump. And that's what this definition is about. So we have some positive number A and some number L. And I would call the Hamiltonian H UAL admissible if it's non-negative, if the support is contained in U, and if, well, on some disk of area little a across an interval of length L, this Hamiltonian is actually strictly bigger than 1. So, well, the point of the L is that I kind of want to cut off the Hamiltonian at time t equals 0 and t equal to 1. So the L kind of guarantees that it was happening in a sufficiently large time interval, and then the A is the area of some disk where the Hamiltonian was at least 1. So these A and L, they measure the size of the support somehow, and L I can think of as being close to 1, and A is some very small number of the area of the small disk that's inside the open set U. Okay, and so now here is the quantitative closing lemma in the special case of the 2-sphere. So the rough statement
interval be separate.
Excuse me?
So in that case, can the interval be separate or just a whole thing? I mean,
about the previous slide, or?
I mean the interval of length L.
Yes.
I mean, is it a whole interval or just a union of separate intervals?
So I think about just one connected interval.
Okay, thank you.
Okay, so the rough statement is written on top, and it says within time delta of our family of perturbations, there must have been an orbit of period at most 1 over delta. And so a bit more precisely, we have our surface, which is the sphere now. It has some total area capital A, and then we have one of our little bump Hamiltonians. And then the theorem says that if delta is sufficiently small, then within our interval from 0 to delta, within that family of perturbations, at some point there must have been an orbit that intersects U, and whose period is at most the floor of A divided by L divided by delta. So if we now make delta very small, then we have a very small perturbation, and that must have produced an orbit of period at most 1 over delta up to some constant. And that, of course, recovers Asaoka-Irie's C-infinity closing lemma, because we can make delta arbitrarily small, and if there appeared an orbit of period at most 1 over delta, they appeared in orbit, and then we have the closing lemma. Okay, so I don't know in general how sharp this 1 over delta behavior is. But one can easily see that if delta is the maximum it's allowed to be in this theorem, the upper bound A over L, in that case, our estimate actually is sharp, because well, if U is very small, then phi, the first couple of iterations of phi could just produce disjoint copies of U. And then if our perturbation just happens inside u, then well, we certainly can't produce orbits of period smaller than the first time u comes back to itself. So on the upper end of the interval for delta, this thing is sharp, and then if delta gets small, we have this 1 over delta behavior, and I'm not quite sure how sharp that is. Okay, but in particular implies the closing.
Can you recall what L is?
L was the.
Maybe you could show the slide, the previous slide with the picture.
So L doesn't show up in the picture. L is the time interval on which we can fit this cylinder underneath the graph. So I guess most of the time we can actually just think of L as being equal to 1. It's more kind of a technical thing that people going to do.
I see. Let's suppose H is time independent, and you're assuming it's. I see. Okay. So we could pretend L is 1, maybe. Did you say? And A is the area that. I see. A is the area underneath the support.
Yes. Okay. And so now, well, I said I want to make the closing lemma quantitative, and also said I want to consider surface maps that might not be Hamiltonian. And before doing that, it's useful to recall this theorem here by Eman. And this says that if we have the two-dimensional torus, and if our area-preserving surface map is a rotation whose rotation number satisfies some diffeomorphism conditions, saying that it's irrational and can't be approximated by rationals very well. Then he showed that for any infinity small Hamiltonian perturbation, the perturbation is going to be smoothly conjugated to the original diffeomorphism phi. And that means in this setting, we can't close up orbits by Hamiltonian perturbations, by small Hamiltonian perturbations, because there's just no orbits that show up at all. Okay, so that means if we just start with an arbitrary area-preserving surface map, and we only allow Hamiltonian perturbations, we can't hope that that produces a closing lemma. But in this example, one can easily see that if we do non-Hamiltonian perturbations, of course we can close orbits. We can just make the rotation angle rational. Okay, so in general, it might happen that one needs non-Hamiltonian perturbations if one's a closing lemma. And, okay, so that's this theorem. And now here is a key actor of the whole story, the mapping torus of the surface map phi. So we take the product of 0, 1 with the surface, and we identify the two sides with the surface map. So this thing is equipped with a vector field R, which is just a partial t, where t is the variable of the 0, 1 interval. And it also, we can define a closed two-form omega phi on it, which on the fiber, which is the surface, is just the area form, and which vanishes on the vector field R. And the flow of this vector field R that encodes the dynamics of the surface. Okay, and so now I want to make the following definition. So this closed two-form omega phi that defines a homology class, in second homology with real coefficients. And I want to call phi rational if this homology class is the real multiple of a class that comes from integer coefficients. So one remark is that this definition only depends on the Hamiltonian isotropy class of phi. So if we take a phi and Hamiltonian perturb it, that doesn't change the fact whether it's rational or not. And second, any phi can be infinitely approximated by rational. So those are dense inside the set of all area preserving maps. Okay, and so now I can state more general quantitative closing lemma. So now we take a phi that we assume to be rational, and the point here exactly is to rule out things like Eman's counterexample, which is not rational. We take a rational phi, and then we take one of our little bump Hamiltonians, and then the statement is quite similar to the case of the sphere. If we take a sufficiently small delta and look at this family of perturbations where tau ranges from 0 to delta, then that had to produce an orbit intersecting U, and the period D is at most 1 over delta. So if the same statement within that time delta, there had to be an orbit of period at most 1 over delta up to some constant. And if I wanted to, I could be very precise about what sufficiently small means and what the constant in the O 1 over delta is. I just didn't want to put it on the slide here, but totally could. Okay, so that's the general quantitative closing lemma. And so a couple of remarks. In the current preprint, there's some kind of technical condition that shows up on the existence of U cycles. I will say more about that later. And so in this version of the theorem here, I actually use a kind of very recent paper by Christopher Gardner, Pomoliano, Prasad, and Zhang, which use Lee Taub's isomorphism between periodic Floer homology and monopole Floer homology and some computation of Kornheim-Rovka to guarantee that this technical condition always holds when phi is rational. So we'll say more about that later. And second remark is that the non-quantitative version of this closing lemma also is proven by Dan, Rogel, and Boyu in their paper, which I mentioned in the beginning of the talk.
So can I ask you a question here? So when you say, I actually can't remember exactly what your statement of the closing lemma was. Was it for generic or dense? But where you're saying that this is something that came up in another talk earlier today. It's a kind of a point of a bit of a confusion for me. You say phi is rational. Now, rationals are dense, but not generic. So this gives you a statement saying densely, the set of symplectic morphisms for which periodic orbits are dense is C-infinity dense, but it's not C-infinity generic.
We'll come to that in a bit. Actually, I think it does prove that it's C-infinity generic. So essentially the point is that if I want to prove that the set of such diffeomorphism is C-infinity generic, I only have to show that for any open set, I can find some perturbation, need not be Hamiltonian, that produces an orbit in that set, and that's enough for showing that C-infinity generically have dense orbits. That will show up in a bit.
Okay.
But yeah, so for now, I just say if I have a rational phi, start with that, and I look at Hamiltonian perturbations, and that's all I'm saying for now.
Right. So for now, the statement just at the moment it just says dense. Right?
Yes. Yeah. So if I start with a rational phi, then well within the Hamiltonian isotopic class of that, I'm going to have a generic set with dense orbits. That's what I'm saying for now. Yes.
Yeah. Okay.
Okay. Well, and now comes the slide I just announced. Yeah. So the first corollary is if we start with a rational phi, then you can look at the Hamiltonian isotopic class of that, and the C-infinity generic element of that is going to have a dense set of orbits. So the Asaoka-Irie proved that that's true for the Hamiltonian isotopic class of the identity, and now that also holds for the Hamiltonian isotopic class of any rational phi. Okay, that's the first corollary, and well, it doesn't contradict Hermann's counterexample because Hermann's counterexample just was not rational. Okay, then the second corollary is actually claim that a C-infinity generic element of the set of all area-preserving surface diffeomorphisms has a dense set of periodic orbits. That's also true. It also does not contradict Hermann's counterexample because there we just restricted to Hamiltonian perturbations, and now I can do arbitrary ones. So this corollary does not follow from the first corollary and the fact that rationals are dense. Those two facts only would give a dense set of area-preserving maps with dense set of orbits. It really is kind of its own argument, but it kind of does follow from.
Maybe we could come back to this later. But what confuses me, I guess I haven't really thought about going from corollary 1 to corollary 2 is that irrational rotations of torus don't have any periodic points. And somehow it feels like you need a rational rotation of torus to get periodic points. Okay. So that's just my comment.
Yeah, maybe actually we can discuss it.
Okay, that's interesting.
All right, so now I want to say a little bit about how periodic Floer homology can be used to prove any of these things. So in this slide, I try to summarize the user interface and the way they're going to use it. So the input is a kind of a closed surface, the area preserving surface map. And then we also take, in the mapping torus, we fix a one cycle, which I call the reference cycle. So this thing, I will talk about the degree of that. And by that, I simply mean, well, a mapping torus is a fiber bundle over the circle, and then just push down the reference cycle and then measure how often it goes around the circle. So that's the degree of the reference cycle. And then if I have my phi and my reference cycle, the output is this periodic Floer homology group. It's a module over a certain Novikov ring. I don't want to go into too much detail about this ring now, but so the idea is that we do keep track of certain second homology classes in the mapping torus. So we have set-mod 2 coefficients, and then we have this formal variable q that's going to show up one more time. And this formal variable in the exponent keeps track of these homology classes. So that's the PFH. It also comes equipped with an endomorphism called the UMAP, and it has an action filtration. And that means that for every non-zero PFH class, we get an associated spectral number, which is just a real number, depending on phi and gamma. Okay, and so here is maybe the most important slide of the start. So that's a summary of our key mechanism to produce orbit closing. And well, the very short summary of this is that a small spectral gap implies orbit closing by a small perturbation. And well, more precisely, we have this key lemma that if we take a rational phi and we take a reference cycle of some degree d, then we can look at a PFH class and we can assume, let's assume that if we apply the U map to that, we get something non-zero. So then we have two PFH classes, sigma and U sigma, and we have two spectral invariants, and we can look at their difference. And that's what I call the spectral gap. So that was what was advertised in the title. So I call that delta. So the U map can't increase action because it's based on homomorphic curves. So this is a non-negative number. And then I claim if I take one of my little pump Hamiltonians, and if I assume the spectral gap wasn't too big, then I can guarantee that if I look at some family of perturbations, that tau now ranges from 0 to, and L is roughly 1, so from 0 to delta, then that family of perturbations had to have an orbit of period at most d intersecting u. And d is simply the degree of the reference cycle. So that's the degree of the PFH we're looking at. Right, so it says, and so that means if we can detect a very small spectral gap in some degree d, then it's possible to produce an orbit by the perturbation that was of order, the size was of order the spectral gap. Okay, and so one corollary of this key lemma is the assertion that if we have a zero, a vanishing spectral gap, then all the orbits had already be closed of period at most d, because then the key lemma says I can produce orbits without perturbing in any open set, so everything had to be closed already. And so this corollary, in fact, is a version of some results that had some very recent results by Christopher Gardner-Mazzucchelli and Ginsberg-Kurel-Mazzucchelli. So they were thinking about rate flows, and they're trying to factorize rate flows with the property that all the orbits are closed. And so what Dan and Mazzucchelli showed is that if we have a three-dimensional rate flow, and if there's some vanishing spectral gap in ECH, then all orbits of the rate flow have to be closed. So they proved the version of this corollary for three-dimensional rate flows. And Ginsburg, Pearl, Mazzucchelli were thinking about also higher dimensional rate flows, and they were looking at other spectral numbers. But there are similar statements that if certain gaps between some spectral numbers vanish, then all the orbits have to be closed. And really, this key lemma, I can think of that as maybe a generalization, an extension of this principle. So now we say if we have a small spectral gap, well, there might be non-closed orbits, but it's always possible to close them up with a small perturbation. And the perturbation, the size is of the order of magnitude of the spectral gap. Okay, so that's our mechanism for closing orbits, and we'll explain more about that later. So, well, now if I claim that small spectral gaps produce orbit closing, well, then I have to, well, show that there are small spectral gaps, otherwise that would be useless. The question is, if we start with some phi, can we always find PFH classes and reference cycles as such the spectral gap is small? Is it possible to find that always? And so here, I'll make the following definition, which is useful for that purpose. So if we take some PFH class sigma, I call that use cyclic if it's true that if we apply the U map sufficiently often, we essentially get back to the same class, but now twisted by the Novikov ring. So Q, that was the variable Novikov ring, and then the exponent, that's a second homology class, and sigma is cyclic if by applying the U map a certain number of times, I get back to sigma, but now with the Novikov coefficient twisted. Okay, and so the reason these U-cyclic elements produce small spectral gaps is that if I have a U-cyclic element, I can apply my U map, and that gives me a whole sequence of these spectral invariants. The U map can't increase action, so with a decreasing sequence of numbers, and then the class was U-cyclic. So in the last step, I in fact know how the spectral invariant relates to the initial one. So this twisting in the Novikov coefficient, that simply drops the spectral invariant by the area of the surface. So it means I have the sequence of spectral invariants. I know the difference between the first one and the last one. I know it's decreasing, and I know how many steps there are in the sequence. So then I know that there must have been a gap whose size is at most the overall difference divided by the number of steps. And that turns out to be the area of the surface divided by the degree, and then there's some correction by the genus. Okay, and so if we have a U-cyclic element in some degree d, roughly we get a spectral gap whose size is 1 over d. And that's then what gives us the 1 over delta and the quantitative closing lemma. Okay, so now the initial question was, are there small spectral gaps? And now I've said the answer is yes, if we can find U-cyclic elements. So then the new question is, are there U-cyclic elements in arbitrarily large degree? And so that's where we use this very recent paper by Dan Rohill, and Hoyu, which essentially says that if we have a rational phi, and if we have a reference cycle, which is monotone, which is just some condition on the homology class, and the important fact here is that if phi is rational, there is monotone reference cycles in arbitrarily large degree. And then this proposition says that then the PFH is actually non-vanishing and all its elements are U-cyclic. So for rational phi, we have a whole lot of U-cyclic elements in arbitrarily large degree. And then by the previous slide, that gives us arbitrarily small spectral gaps. And then by the key lemma, that's what produces closing lemmas. Okay, and so this proposition, it's based on, first of all, so Lee Taubes have isomorphism between PFH and some version of a monopole Floer homology. And they observed that in large degree, this PFH actually is isomorphic to a version of this monopole Floer homology that does not involve any irreducible monopoles, and then Kronhammer-Mofka have in their book some spectral sequence to compute that, and then Vogel and Boyu worked all of that out, and then they told us there always is U-cyclic elements. Right. Okay. So that's a rough summary of how we prove our closing lemmas, and so now I want to go into some more details on what PFH is and how to prove any of these claims about it. Okay, so yeah, so now we take surface map phi, and let's assume for now that it's a non-degenerate surface map, meaning that all its periodic orbits are non-degenerate. And then I will make a couple of definitions. The first definition is that a PFH generator that's going to be a finite set of simple closed orbits, and I can view them as orbits of the surface map or as orbits in the mapping torus. These orbits are equipped with integer multiplicities, which are positive, and we in addition impose that they go to 1 whenever the orbit is hyperbolic. So such a finite collection of orbits of multiplicities, that's a PFH generator. So then, well, we want to define action, and if we just have this PFH generator, well, it doesn't really have a natural action defined. And that's why it's useful to actually consider anchored PFH generators. And by that, I'm going to mean a PFH generator alpha together with a relative homology class set that goes between alpha and the reference cycle. So really, it's a 2-chain whose boundary is alpha and gamma, and then I look at those modulo homology, and then it's an anchored PFH generator. And one of the purposes for considering these anchored generators is that now we can just define the action to be the integral of our closed 2 form omega phi on the mapping torus over the anchor set. And then we have this action of an anchor generator. Okay, so now we know what an anchor generator is. We can define the PFH. So the chain complex it's going to be consist of all formal linear combinations of these anchor generators with set mod 2 coefficients. So these can be kind of infinite linear combinations, but there's a finiteness condition that for every action level, there's only finitely many generators above that. So that's the underlying vector space or module. Then all I want to say about the differential is that that's defined by counting geomorphic currents inside the symplectization of well, either you can call it ECH index or PFH index 1. And well, we have these kind of anchors and the Novikov ring, so really also keep track of the homology classes of these geomorphic currents. The UMAP also involves counting geomorphic currents, now of PFH index 2 with some point constraint. And well, then if we take the homology of this complex, then it follows from Berkeley and Taubes that actually didn't depend on J, and so we get this well-defined module only depending on phi and gamma, and it has this endomorphism U. Okay, so we are interested in spectral invariants, and here is how those are defined. So kind of all of our anchor generators, they have an action. So if they're given a non-zero class, we can ask what is the minimal action it needs to represent this class by our anchor generators. And that's how this spectral invariant is defined. And I call that C sigma of phi and gamma. Okay, and so well, a priori that's defined for non-degenerate diffeomorphisms phi, and then but it turns out that they are over continuous, and then we can continuously extend the spectral invariants to also degenerate phis. And the important lemma here is that these spectral invariants, they actually measure something useful. So the lemma says if phi is rational, then if we have a spectral invariant, that number is actually equal to the action of some anchored PFH orbit set. So that's a meaningful number. So this rationality hypothesis here, it might be removable. The problem is if phi is not rational and degenerate, then we don't quite know whether we can actually remove it. But we really only need a number for rational phi's anyway, and there, no matter whether phi is degenerate or not, we always have this representation of the spectral invariants by actual anchored orbit sets. Okay, and so now let's think about Hamiltonian perturbations, how the PFH depends on the Hamiltonian perturbation of the surface map phi. So I want to consider the symplectization of my mapping torus y phi. I put a symplectic form on that, which on the surface fiber is just the area form, and then I add ds/dt to that, where s is the symplectization direction and t is the direction of the mapping torus. Okay, and so now it will be useful to think about Hamiltonians as actually smooth maps which are defined on the mapping torus. So if we have such an H, well, the mapping torus was 0, 1 across the surface modular equivalence relation. So if we have such a smooth function mapping torus, that we can just regard as a time-dependent Hamiltonian. And it will be useful to also impose the condition that at time 1, the Hamiltonian kind of pulls back to time 0 via phi. So I want to impose it as a smooth function on the mapping torus. Okay, and if we have such a smooth function, we can look at the graph of it, and I want to think of that as lying inside my symplectization. So then we have a 4-dimension 1 hypersurface inside the symplectization, so it has a characteristic foliation, and one can check that if we look at the flow of this characteristic foliation on the graph of H, then the return map is exactly equal to the Hamiltonian perturbation of phi. So that means if I take this H and look at the graph, I can really identify the graph with the mapping torus of the Hamiltonian perturbation. So whenever we have mapping torus of Hamiltonian perturbation, I think of that as lying inside my symplectization as the graph of the Hamiltonian. Right, so if I have a reference cycle in the original mapping torus, that naturally gives me a reference cycle in my Hamiltonian perturbation by just moving it in the symplectization direction. So I try to indicate that in my little picture on the bottom. And moreover, if we have now 2 Hamiltonians, H1 less than H2, then we can look at the region in between the 2 graphs. And now that's, I want to regard that as a symplectic cobordism between the 2 mapping tori. Right. So really all my Hamiltonian perturbations, the mapping tori of that, I think of them as lying inside the symplectization. And then whenever one Hamiltonian is less than the other, I have the symplectic cobordism. And I also have a natural way of producing, of moving the reference cycles around. Okay, and so now, well, with all these symplectic cobordisms, using work of Lee and Taubes and also Chen, these produce cobordism maps of PFH. And now the nice fact is that they're all very compatible with each other. So they're compatible with respect to composition. If we have H1 less than H2 less than H3, we can compose, and then it composes well. If I simply move a Hamiltonian by constant, I get back the exact same mapping torus, and in that case, the cobordism map is the identity, and also these cobordism maps, they commute with the U map. So really, this way, I can kind of naturally identify all the periodic Floer homologies of all the Hamiltonian perturbations of my original phi. Okay, and so now if I start with a PFH class in the PFH of the original diffeomorphism phi, then I can look at the PFH of the Hamiltonian perturbation, and then via my isomorphisms, that gives some corresponding PFH class. I can call that sigma H. And that means I have the spectral invariant C associated to sigma H, phi H, and gamma H. And to make the notation a bit less awkward, I call that C sigma of phi, gamma, and H. So at this point, if I fix a PFH class and a phi and a gamma, I can regard my spectral invariant as a function from these Hamiltonians to real numbers. Okay, and so now we want to prove some things about these spectral numbers. So here is kind of the main ingredient for proving some estimates on those. And that's very similar to what also happens in the Weil law for embedded contact homology. So I guess the first version of that Weil law, Michael proved it for star-shaped hypersurfaces inside R4, and there this Weil law is not purely proved by backing balls inside certain symplectic coordinates and then proving some inequalities between ECH capacities. And really what I want to do here is I want to do the same kind of argument, but now for PFH spectral numbers. So a bit more precisely, if I take two of my Hamiltonians, H1 less than H2, again, inside the symplectization, I can look at the symplectic coordinate between the associated mapping tori, and then I can put symplectic balls inside there. And then I can make the statement here, it's an equality about how spectral numbers change. So the rough idea, and well, one can probably make sense of that, and it's not exactly how it's technically implemented in the paper right now, but the rough idea is that if we have this symplectic coordinate between the mapping tori and we put these balls inside there, we can really view it as a symplectic coordinate where on the top end we have the mapping torus of the Hamiltonian perturbation by H2, and on the bottom end we have the mapping torus of the Hamiltonian perturbation by H1, disjoint union with the boundary of these balls. So on the top end we just have the mapping torus, which is stable Hamiltonian manifold, and on the bottom end we have the disjoint union of these contact manifolds, the ball boundaries, and another mapping torus, the stable Hamiltonian manifold. Right, and then if one imagines that this coordinate should produce a coordinate map, that would go from the PFH of H2 to the PFH of H1, and then tensor it with the ECH of the boundary of these balls. Right, and then the important fact about these coordinate maps is that, I mean, they're defined via Savage-Witten theory, but kind of any non-zero coefficient in this coordinate map, it can always be represented by an actual holomorphic curve, so it cannot increase action. So whenever this coordinate map takes some class in the PFH on the left side and it maps it somewhere, it can only decrease the action. And that really is what encoded in this ball backing inequality up there. So we have some PFH class sigma, and we look at the spectral invariant of sigma with the U map about a couple of times with respect to H1. On the right, we have the spectral invariant of sigma with respect to H2. There's some correction term in terms of the reference cycle. So if we imagine that the reference cycle is outside the support of H, that would vanish. And then there's some ECH capacity of the balls. So we have this inequality, and it really is pretty much analogous to similar inequalities one gets when proving the ECH value. Okay, and so now.
So Oliver, I have a quick question. So you can so I assume you can try something like this in the ECH case, but you don't have this U cyclic property. So you only get a bound in one direction, I guess, for the spectral numbers. And then the cyclicness gets you bounds in both directions in the setting.
So, well, Okay, so I guess for ECH, so first Michael proved the Weil law for star-shaped hypersurfaces in R4. And I think really the point here was, if I have that, I can put a ball inside and I can fit a large ball around. So I squeeze the hypersurface in between two things where I know everything. And here the point is I can do a similar thing. So I have two Hamiltonians, and I can always move one by a constant up and down. And well, I'm reading very vague here, but that kind of what gives both inequalities here. So I think in the ECH value for general contact manifolds, because the main problem is there's kind of nothing we can put above our given contact manifold, which we understand. So then it becomes more complicated. But yeah, here we can, and then the ball packing inequality is actually two inequalities. The point here is we can if we shift H1 by constant up, we can interchange the role of H1 and H2, and we get a reverse inequality.
Great, thank you.
Right, and so now I want to give a brief sketch of how this key lemma comes out of that. So the key lemma was saying a small spectral gap gives orbit closing by a small perturbation. So I've written down the key lemma one more time here. Right, so we start with a spectral gap of size delta, and then I want to show that if I look at a perturbation of size delta, that must have produced an orbit of period at most d, which intersects ours at u. The first observation here is that if I look at the cobordism between the mapping torus of phi and the mapping torus of the Hamiltonian perturbation, so now I take h and I multiply it by the size of the spectral gap. Inside that cobordism, I can fit a ball of area bigger than delta. So that's the whole point of these new AEL admissible Hamiltonians. I want to guarantee I can fit balls underneath the graph. Right, and so here I can fit a ball of size of area bigger than delta, because we know that this h was bigger than 1 on some set with size I can control, and then if I multiply h with delta, then it's bigger than delta on some set of controlled size. Okay, that's the first observation. Then the second observation is, so now let's assume that the lemma is false. Let's assume that we have this family of perturbations where we go to perturbation size delta, and let's assume no orbit ever showed up at all. Then I claim that the spectral invariant before and after perturbation is the same. And the reason here is that, well, we have this action spectrum, it has measure 0, and if there's no new orbits, then it just stays constant. And we know that spectral invariants are continuous. So if we have a continuous function that takes values in this constant measure 0 set, it just had to be constant. Right, so if there's no new orbits, the spectral invariants can't change. That's the second observation. And now I want to go to the contradiction together with the ball packing lemma. So the first observation, which said we can put this ball of area bigger than delta in the cobordism, plus the ball packing lemma gives me this inequality here, where the spectral invariant of u applied to sigma is bounded above by the spectral invariant of sigma perturbed by my Hamiltonian, and then minus the ECH capacity correction. Now I have this inequality, and if I combine that with the second observation that the Hamiltonian perturbation doesn't change the spectral invariant, and then move the ECH capacity to the left side, what I get is that well, the first ECH capacity of the ball, now that's delta plus epsilon, is less than or equal to, and we get exactly the spectral gap delta. Right, and then, well, it's well known that epsilon is bigger than 0, so that's a contradiction. Right, so, and now that gives me this key lemma that I have a spectral gap delta, and my perturbation goes up to that size, then I have to have a new orbit. because they can fit the ball in, and if there's no new orbit, they have the spectral invariants don't change, and then that would contradict the ball bucking lemma. Okay, and so that's kind of the rough idea of this key lemma, that small spectral gaps give orbit closing by small perturbations. Yeah, and then, well, since I explained that there always exist sufficiently many arbitrarily small spectral gaps, then that gives the closing lemma and the quantitative version of that. Okay, so that's pretty much what I wanted to say about the proof. So I have one more slide here, and that's about the PFH while law. So that really is a statement that's pretty much analogous to the while law in ECH. So here, if we take a rational Eric-Certain surface map, let's assume we look at a sequence of reference cycles, gamma k, and we assume that their degrees, the degrees go to infinity, and we assume that they're all monotone, which is some condition on the first homology class. And the important fact here is that there's monotone reference cycles in arbitrarily large degree. Then if we also look at a sequence of non-zero PFH classes, and well, the existence of such a sequence is guaranteed by what Dan, Rogel, and Boyu showed, then in that situation, it's true that for any Hamiltonian H, we can recover the integral of H, the Calabi invariant of H, by the amounts the PFH spectral invariants have to shift. So on the left side, we have the unperturbed spectral invariant. We have the spectral invariant perturbed by H. So we take the difference of that. And well, if we ignore this integral over the reference cycle of H, well, we can think for now that the reference cycle is disjoint from the support of H, then that will vanish. So in that case, this difference normalized by the degree of the reference cycle in the limit gives us back the integral of the Hamiltonian. Right, that really is very analogous to the ECH while law. So because well, the ECH while law, the ECH spectral numbers recover the contact volume, and so the Calabi invariant of this Hamiltonian really is something that one can interpret as a volume. For example, in the open book construction, the Calabi invariant of the surface map would exactly be the contact volume, and we have the statement here. So again, it's a couple of remarks I need to make. So Dan, Rogel, and Boyu proved this result a different method, not using this ball backing approach of ours. Also, the way I stated this result here, I removed some technical revision we have right now in our current preprint, using this result on the existence of U cycles. And third remark is that this while law also implies the closing lemma, maybe not the quantitative version, but it implies the closing lemma, because as soon as we have perturbation that a Calabi invariant is non-zero, that while law says spectral invariants have to move, and then there have to be some new orbits. And well, in addition, this while law also has some in addition to the closing lemma, there's other very interesting applications of this PFH while law, which have appeared very recently. So there have been very interesting papers by various subsets of Dan and Demoliere, Max, Seferdini, and Smith on C0 symplectic geometry. For example, they resolved the simplicity conjecture, and that uses essentially a special case of this while law. One can study the large-scale Hofer geometry of Hamiltonian surface diffeomorphisms, and also recently there's was a paper on linked spectral invariants, which also is a set of spectral invariants that recovers the Calabi invariant, and then one can use that to extend the Calabi invariant to non-smooth Hamiltonian diffeomorphisms. And so here, this PFH spectral numbers, this file law shows that they can also be used for that application. So they have this very similar property of recovering the Calabi invariance. Okay, but so I guess that would be the topic for a whole different talk. So this talk really was focusing on the closing lemma, and the while law gives the closing lemma, and but it turns out one doesn't even need that much of it. The while law is much stronger than one needs for the closing lemma. Okay, so that's why I put it just on the last slide. Yeah, so that's pretty much everything I wanted to say. So thanks everyone for listening, and thanks again for inviting me.
Let's thank our speaker. Thanks very much. Any questions for Oliver?
So can I ask a question?
Yes.
You needed to know that certain homology classes were non-zero, and everywhere you had this, you had also the assumption that if you go back, for example, to your last line, you have phi is rational, starting assumption.
Mm-hmm.
So the rationality of phi guarantees non-zeroness of periodic Floer homology.
Yes. If phi is rational, we can find reference cycles in up to a large degree such that the PFH is non-zero. Yes.
And if it's irrational, it's zero? Or?
Well, I mean, if we, for example, look at some irrational rotation of the torus, then there's no orbits, and then the PFH would vanish. Well, I guess we haven't worked this out, but one can also try to, one can also maybe do some constructions in higher genus where we look at some one form with only kind of index 1 critical points and make everything kind of sufficiently rational, and then because the PFH doesn't, hyperbolic orbits we can only take with multiplicity 1, then we could also try to cook up something where in large degree the PFH has to vanish. So that clearly happened that for irrational phi's PFH is 0, and then we can't see anything.
Right. Okay. Okay, thanks.
So could it be that there's some more general statement for sort of 3 manifolds that generalizes both, the closing lemmas for maps of surfaces and also contact 3 manifolds, like some very general stable Hamiltonian version of the closing lemma?
Well, I haven't thought about this question. I mean, in principle, yes. Yeah, I really haven't thought about this, but in principle, yes, that could really happen. So also like this key lemma that small spectral gaps imply orbit closing, that I could really imagine holding bigger generality even for other kinds of spectral numbers. The real question is, when can I guarantee that we have small spectral gaps? And well, I guess the only examples I know now is the ECH capacities because of the sublinear growth, which forces small gaps, and now the PFH because we have this U cycles. But yeah, I mean, I could imagine that it's the case. Yeah, to an extent that.
So Kyle, you mean like every rate flow flow of a stable Hamiltonian structure satisfies the closing level?
Yeah, I was just wondering, could there be something like that that implies the 2D case where you say like, okay, you take that sort of mapping torus and then some perturbation of that induces some perturbation of the mapping torus, and then just by some general result, you know that that has to have a
Okay,
dense orbit. Or...
I see. I was just trying to understand the question. That makes perfect sense, the question. That's nice.
I think Fish and Hofer in their recent preprint conjecture to closing lemma for general hypersurfaces in R4, just looking at the characteristic foliation, which is not necessarily even a ray vector field. I had some ideas about using feral holomorphic curves to approach this.
I see, and this would imply, okay, for maybe this is just for domains in R4, but would this imply special cases of both the surface closing lemma and the ray flow closing lemma?
But there has to be some sort of a condition on the hypersurface. No, there's another one of these Hermann counterexamples, or I can't remember off the top of my head.
In dimension 4, there's a C2 counterexample, which I think has been, I don't think it's been written this way, but maybe it can be upgraded to C2 plus alpha. So like oh, sorry, not a counterexample, the closing lemma. There's a counterexample, like there's no periodic orbits on this hypersurface.
Yeah,
I think so. I think in terms of your, so I didn't actually answer your question, perhaps, but I think that's the most people know about that.
Sorry, I didn't understand what you said. You said there is a C2 closing lemma?
No. There's a C2 hypersurface in R4 whose characteristic foliation has no periodic orbits.
All right, but then,
Yeah,
I mean, but then you have to perturb it.
indeed. Yeah.
There's certainly, this Hermann produced a whole bunch of counterexamples to the closing lemma. It's just that one has to read the, hypothesis carefully to see where it applies and where it does not apply. But my impression was that he did produce some sort of counterexample of closing lemma for hypersurfaces, but maybe I'm mistaken. I can't remember the statement off the top of my head.
I remember seeing such a thing. I don't remember the details either. But I think it's not like a hypersurface inside of 4. It's more some hypersurface.
Maybe you're right.
okay, maybe I can sort of add to that, because it's actually a C2 smooth hypersurface in R4, and it's Bashak and myself. And Irman, I think, produced high dimensional counterexamples, and myself too. But of course, these things are very unstable.
To the cipher conjecture.
Yes.
That was a question, Victor.
Say it again.
So I thought you produced hypersurfaces without periodic orbits.
Yeah. And what was the question?
The question was, can you produce some counterexamples to the closing lemma for certain classes of hypersurfaces? But
no, because of the, what is it called? Because of the almost existence. So when you have a shell, when you have a family of hypersurfaces, then almost all of them will have aperiodic orbit.
Okay.
So,
But that certainly doesn't imply the closing lemma, right? Because the orbit could be anywhere, I suppose.
No, it does not imply the closing lemma in that sense. It just implies like a
existence of a periodic orbit.
Generic existence of periodic orbit.
Can I also just ask, so this Hermann, people keep mentioning this Hermann example, which I guess they also imply in higher dimensions, right? This sort of irrational Diophantine rotation.
Yes.
But
I think this is actually how he stated it. I think the original statement was like for a hypersurface in an irrational four-dimensional torus. It works like in all irrational tori of all dimensions. And maybe in some other manifolds one can actually do it too, but they all have to be like very irrational. There should be like enough one-dimensional cohomology there.
Right, so some sort of Diophantine condition on the,
Mhm.
yeah.
So I just wanted to ask, so if you just impose the same rationality condition from this talk on the, on the mapping torus, then is there still kind of a counterexample, or could there be a C infinity closing lemma in higher dimensions with that rationality assumption?
I don't think it's known.
Okay, so but there's no counterexample then.
No. I think they all are, yeah, sufficiently irrational.
Extremely rational.
Mhm. It's kind of peculiar because on the one hand, they're irrational, but on the other hand, they're, I think, Liouville, right? So they're actually kind of close to
they're
being
Diophantine.
but I
It's a
might be wrong.
Diophantine condition, so it's somehow they're not generic in some sense, but I can't remember off the top.
Yeah,
of my head.
I don't quite remember.
Yeah, there are some technical statements that were proven by Hermann. But, sorry, some counterexamples were produced by Hermann, but one has to check whether, so what they imply in a specific setting one is looking at. So Oliver, we had kind of, there was this, we had a brief discussion at the beginning of the talk about the actual closing lemma. We says, as you said it at the beginning, you have like a periodic, you have a point, a recurrent point that comes very close, back very close to itself. The goal is to, there's the point and the point after time n for large n. And the goal is to make a small perturbation to close the orbit. So meaning you find a periodic orbit that stays very close to the initial period. Now, the statements you stated today say you take that initial periodic point, you make a perturbation, and you find some periodic orbit that passes through the open set nearby. But this new periodic point outside the open set might just be elsewhere in the manifold, the periodic orbit. Yeah, you find a periodic orbit, you don't know if it's close to the initial periodic orbit that you started with. I think. I mean, maybe I'm mistaken, but that's my understanding.
So I wasn't.
So what you said about conjugating creates a periodic point that passes through that point, but it doesn't create a periodic point that stays close to the entire orbit.
Okay. Yeah. Well, I was
Got a periodic point that went like
considering that requirement.
And now you created one that might go elsewhere in the manifold and come back.
Okay. See, that I would have to think about whether I can actually guarantee that the new orbit is like close to the initial trajectory all the time. No, I have to think about it.
I have vague memories of dynamicists saying that it's probably false or something. So that's why I was.
Okay. So I did not want to claim that. I did not have this requirement in mind. So that I have to think about. Yeah.
I think there may be a confusion here, because when people say the closing lemma, they actually refer to two different things. One is, as Sobhan said, a process that closing up a given orbit, and this is, I think, what Johan and Robinson did. And another one is a consequence that you can, by a small perturbation, you can make the set of orbits dense. But these are actually sort of two different statements. One follows from the other, and I think what you prove and actually Irie proved is the generic C infinity generic existence, but not, it's not a process of closing up one order. So these are actually two different things slightly.
Right, that's my understanding as well.
And you're saying this, the stronger version is not known for rate flows or surface morphisms. It might even be false or C infinity.
Yeah. As far as I know, the stronger statement is only known for
C1.
Yeah.
It's
And,
actually even that a little bit non-trivial, because kind of one still should check when they make this, when they run this process, it's actually in the C1 class. So one should, in addition, check that you can actually make it C infinity smooth. C1 small, but C infinity smooth. And I think it's true, but it's kind of not immediately obvious. It's not exactly on the surface of things. Like you don't want your vector field to be, or your map to be just C1. You want it to be C infinity.
Ah, I see. You want to find a C infinity closed by a C1 closed by C infinity.
C1, C infinity smooth.
Yeah, C1 perturbation with C infinity smooth. Yeah.
I think this would maybe be a good time to end the official discussion, the official Q&A, and thank our speaker, Oliver, again for a great talk.